The Pacific Ocean currently appears stable. It is sitting in what meteorologists call ENSO-neutral conditions, with water temperatures across the equator remaining close to their long-term averages. Below that calm surface, however, heat has been building for months. Models now show an 82% probability of an El Niño emerging between May and July 2026, with some projections reaching anomalies of 4 degrees Celsius, values that would sit at the extreme end of the historical record. This shift is already manifesting in the immediate present. We are beginning to see the atmospheric precursors of a major event, with storms starting to organize across the basin. This forecast bulletin from the Climate Prediction Center indicates enhanced chances for tropical cyclogenesis, the birth of cyclones, in the western Pacific during week 2 and the eastern Pacific by late week 2. To understand why these storms are forming now and how they contribute to a global heating cycle, we have to track the intersection of two massive systems, an underwater wave of heat and a high-altitude wave of pressure. The Pacific Ocean operates as a heat engine. Standard trade winds blow west, pushing warm surface water toward Indonesia. As warm water moves, deep cold water rises near South America to replace it. This upwelling maintains the temperature gradient defining the neutral Pacific. In early 2026, that engine was disrupted. A triplet of tropical cyclones in the western Pacific produced strong westerly wind bursts that reversed the normal trade winds, mechanically pushing that warm surface water back toward the east. This reversal effectively loaded a massive volume of warm water into the central and eastern Pacific, providing the initial fuel for the coming climate shift. That displaced warm water travels as a subsurface feature called an oceanic Kelvin wave, a deep water pool of heat moving steadily toward South America. This specific wave's scale is noteworthy. Data shows heat anomalies up to 8 degrees Celsius, concentrated between 50 and 150 meters deep. As this wave propagates eastward and reaches the South American coastline, it is forced upward, bringing this deep heat reservoir to the surface. While this surfacing heat provides the raw energy for an El Niño, the transition remains incomplete without a specific response from the atmosphere. The second piece of this puzzle is found in the upper atmosphere, the Madden-Julian Oscillation, or MJO. The MJO is a traveling band of wind, rain, and pressure that circles the global tropics. It moves in a predictable cycle, shifting between phases of enhanced and suppressed precipitation. In early May, this signal stalled over the Indian Ocean. This chart shows disorganized velocity potential anomalies refusing to move, disrupting normal progression. But that stall has ended. The MJO is propagating eastward again, moving directly toward the warming Pacific. This creates a direct convergence. The atmospheric storm band of the MJO is migrating over the exact region where the oceanic Kelvin wave is reaching the surface. When these two waves align, they enter a state of constructive interference, where the atmosphere and ocean begin to reinforce one another. We can track this coupling through the Southern Oscillation Index. The index has fallen to -11, indicating the atmosphere is actively responding to rising oceanic heat by further weakening the trade winds. Simultaneously, the ocean has crossed its own threshold. This Niño 3.4 index shows the moment surface temperatures spiked into positive territory, confirming the transition out of the neutral phase. This verified ocean-atmosphere coupling is what provides the energy for the tropical cyclones forecasters are now predicting for the central and eastern Pacific. With these two systems beginning to work in tandem, the standard Walker circulation is weakening, and El Niño conditions are becoming established across the basin. While the global mechanics are predictable, the local consequences often produce outcomes that seem contradictory. India provides a clear example of this complexity. An emerging El Niño typically suppresses the summer monsoon, with forecasts for 2026 predicting below normal rainfall at just 92% of the long-term average. However, the ground reality in early 2026 has been the opposite. Because the MJO stalled over the Indian Ocean before reaching the Pacific, it triggered unusual storms and cooling across India, leading to floods instead of the expected pre-summer heat waves. Adding to the complexity, a positive Indian Ocean dipole may develop later this monsoon season, which could partially offset the drying effect of the El Niño in certain regions. These local variations show that while the Pacific sets the global stage, the specific timing and movement of atmospheric waves determine the actual impact on the ground. The global climate is a system of interconnected parts where oceanic heat and atmospheric pressure work as a single integrated machine. We are tracking forces of immense scale, an atmospheric band of storms moving in tandem with a heat reservoir that extends from 50 to 250 meters below the sea surface. By monitoring the intersection of the deep-sea Kelvin wave and the high-altitude MJO, researchers are moving beyond general observation toward a more mechanical understanding of how the 2026 El Niño will reshape our global weather.